Well, last time we discussed some general Langland's philosophy with the mathematical principle. For a field K, G group over K representations of G of K should somehow correspond to homomorphisms from the Galois group of K, the absolute Galois group of K, into the Langland's dual group of G. So this is a very vague formulation, and maybe it's never true as stated. Notably, one say K is complex numbers. Yeah, then this Galois group is trivial, so there is nothing on the right hand side. Or one K is the field of real numbers. Now the Galois group is just Z mod 2Z, and still this is too small. But still it is possible in very many instances to make a precise statement and even prove it in quite a few cases. Okay, so this was the main takeaway from the last time, and also there was sort of lifting from finite characteristic to the zero characteristic. Proposition we proved last time for a finite group. And a representation rho from G to GL K, and K was of Q, finite characteristic field. Then Ui of X are eigenvalues of rho of X. Oh, sorry. And F symmetric function integral value. And the claim is that chi, which sends x to the symmetric function of theta of u1 of x, and so on, theta of un of x, is an integral. This is the key point. Linear combination of characters G, and complex characters. In characteristic 0. And here theta is a character from the demonstrated group of the algebraic closure into complex numbers. Okay, so this was the lifting proposition we proved last time, and today we will apply it to the construction of integral lattice in the central functions from GLN itself. So we'll apply it to the case G equals GLN, okay? And we'll construct the desired integral lattice of characters. Okay? In all the complex relative central functions, we will construct the lattice of integral combinations of the actual characters. Okay, so now G is Gn. So representation rho will be the identity representation into itself. Our function f will be the elementary symmetric function ER, and theta will be assumed injective. Well, this is possible to do because M is a union of cyclic groups. You just extract roots and roots and roots for unity. So then we get chi r as here. Elementary symmetric function of theta over x1, so on, theta of xn. So these are just xi eigenvalues G. So they lie in this group M. Okay. And there's a complex character, meaning integral linear combination of characters of complex representations. Okay. And the characteristic polynomial G G is the product of T minus eigenvalues equal to the product over all irreducible polynomials, the corresponding polynomial to the power of the corresponding partition. So mu is corresponds to the conjugacy class of G. Yeah, we discussed last week, or even before, that the conjugacy classes are numbered by multi-partitions. Okay, so now given f, the product of t minus yi, we set, and this notation that will be used throughout. I don't know the English name for this. Курс повышения квалификации, how do you say in English? And even Savbak, I don't know how to say in English. So the mathematics department has two parts, mathematics and pedagogics, teaching, high school teacher, for high school teachers. and then they offer some lectures for the existing high school teachers.
Moscow?
In just Moscow high schools. So the teachers from all over Moscow come here to these lectures. F tilde is defined as the product of 1 plus yit. So the roots here are yi, but the roots here are minus yi inverse. Okay. And theta of f tilde is the product of 1 plus theta of yi t. Okay, so I hope to save this notation for a while. So we have the sum of chi r of g t to the power r. Since chi r arises from the elementary symmetric functions, we have this is equal to the product of 1 plus theta of xi eigenvalues times t. Yeah, just the generating function for elementary symmetric functions. And it follows that the sum of chi r of g t to the r equals the product over all irreducible polynomials, theta of phi tilde to the power the size of mu of f. Okay, so we'll save these two formulas. Oops. Okay. Now we have chi r is a certain linear combination of the delta functions of conjugacy classes. So this is just a characteristic function. Of conjugacy class. Okay, and so we see that the sum of characteristic functions of chi r times t to the r is the sum over all multi-partitions of the size n, product over all the polynomials, irreducible polynomials, theta of f tilde to the power size mu of f times p. So these are again mu of f. So these are multivariable, so to say, whole Littlewood functions, and well, just by construction, by definition, they corresponded to the delta functions of conjugacy classes. So this is sort of tautology, and well, maybe we need to remember this tautology as well. And now let's prove a combinatorial lemma that has nothing to do with our characters. The sum over all partitions of size m, t to the power n of lambda, whole Littlewood function p lambda of x and t equals the complete symmetric function hm of x. Okay, so it has nothing to do with current business, but we'll use it later on. And in fact, it is even it was given as an exercise, but since nobody yet solved this exercise, maybe let me give a proof. Okay. So let's consider the sum over all mu, the structure constants g lambda mu 1 to the power n, or m rather, sorry, m, of some interpolation ring. So these are structure constants in the whole algebra. So number of submodules are given type and cotype in this. Okay, so this is the number of elementary submodules of type 1 to the power m, so trivial submodules in the circle of n o module m of type lambda. Okay, and this is equal to the number of points in the Grassmannian, L of lambda, choose m, QQ binomial coefficient of Q. First, m-dimensional subspaces in the circle. The circle is L of lambda dimensional space over our ground field. Okay, now the structure constants in the whole algebra are related to the structure constants of the symmetric algebra in terms of whole Littlewood polynomials in the following way: minus n of mu minus n of 1 to the power m f mu 1 to the n lambda and of Q inverse. So these are structure constants in the whole Littlewood basis. lambda t. Okay, we conclude that the sum over all partitions mu, t to the power n of mu, structure constants f mu 1's lambda of t equals t to the power n of lambda minus m choose 2, the Q binomial coefficient of T inverse. Okay. Now take a new variable y and consider the product sum of t to the power n of mu, p mu, that's what we want, times the sum over m, e to the m, y to the m. And recall that e to the m, em is exactly the whole polynomial corresponding to ones, yeah, m ones. Okay, so this is equal to the sum over lambda, mu, and m, y to the power m, t to the power n of mu, f lambda mu 1 to the power m over t times p lambda. Okay, and well, this is equal to this is equal to the sum over lambda, t to the power n of lambda, p lambda, the sum over m, y to the power m, t to the power minus n choose 2, times the Q binomial coefficient of T inverse, and finally this is equal to the sum over lambda, t to the power n of lambda, p lambda, the product over 1 plus t to the power of 1 minus j times y. Okay. And the last equality is just the Q binomial, well, Newton Q binomial. Namely, the product over 1 plus t to the I y is the sum minus 1 to m t to the power n choose 1 the binomial coefficient y to the r. Okay, and this you can prove just by induction. And in m degree. And that's you see if t equals one, then we get just the usual Newton binomial, right? And this is sort of Q binomial. Okay, only I still didn't prove our lemma. What shall I do? Okay, maybe let me move this up. Okay, so now we can specialize y equals -1. And what do we get? We get the sum over mu, t to the power n of mu, p mu, times the sum over m minus t to the power m em, and this is equal 1. But you see, this is an inverse function to the generating function of complete symmetric functions. And so we get that what we want. Okay, so the lemma is proved, and here is the lemma, and here is the corollary. That the sum over all partitions of size m, p tilde lambda of f, is hm of f for any irreducible polynomial f. And well, this was again from the last week when we introduced polynomials in many groups of variables numbered by irreducible polynomials. And so now the conclusion is that sorry. Yeah. Here we have this identity. And the right-hand side of this identity is the sum over all sort of compositions. Alpha, the product over all irreducible polynomials, theta of f tilde to the power alpha of f, h alpha of f so here the sum runs over all functions from irreducible polynomials to positive integers, such that the sum over f, degree of f, times alpha of f equals m. Okay, so in other words, the right hand side of our formula is the coefficient of u to the power n in no. In the generating function h of tu is the product over all irreducible polynomials, product over all positive integers, 1 minus theta of tilde x I f, variables in group f, times u to the power degree of f. Okay, and the conclusion is that the coefficient of t to the power r, u to the power n, in h tu equals the heuristic map of chi r. So in particular, sorry, chi r. Sorry. In particular, this coefficient aligns in the integral lengths in well, I think it was called B. Yeah. Okay. So we have introduced some symmetric functions counting our characters, and well, so there were some complex linear combinations of characters, but this guy, this coefficient is the integral coefficient, an integral linear combination of characters. Okay, and now we'll rewrite this coefficient in some other form. So we'll rewrite h of tu in the exponential form. So we compute the logarithm. The sum over irreducible polynomials over positive integers, logarithm 1 minus theta over tilde x I f u to the power degree f inverse again the sum over positive integers, 1 over m, the sum over irreducible polynomials, theta of f tilde to the power m, power sum of this group of variables u to the power m times degree of f. And now if x is a root of f, then theta of f tilde is the product from 0 to the degree of f minus 1, 1 plus t theta of Frobenius to the power I of x. Since all the roots are interchanged by the Galois group. Galois group is generated by Frobenius automorphism. So d is the degree of f. And Frobenius to the power d applied to any root is x itself. So the Galois group is the cyclic group of order d. And hence theta of f tilde to the power m is equal to the product from I equals 0 to m times degree minus 1, 1 plus t theta of Frobenius to the power ix. And hence we can rewrite the logarithm of our counting function as the sum over all positive integers u to the power m over m, the sum over degree m multiplicative. So sorry. Yeah. So the maybe I should write k. The degree m extension multiplicative group. Well, it only gets worse. And I forgot how to erase. Like this? No. Unfortunately, no. Yes. Great. No. So I don't know what to do. Oh, great. No more luck. Okay. So I wanted the multiplicative group of degree m. Sorry. Yeah. And here I take the modified power sum function. I will recall the moment. What was it? Times the product from 0 to m minus 1, 1 plus t theta over Frobenius to ix. Okay, so this modified power sum function was p tilde m of x was either p to the power p m over d of f if m was divisible by d or 0 otherwise. Okay, and here f was the minimal polynomial of x. Okay, so that's what we that's what we get. And we, no. So I guess I need a new blackboard, right? But unfortunately, maybe then I'll repeat what we were trying to do. So we're rewriting this counting function h of tu in exponential form, logarithmic form. But maybe somebody knows how to recall this previous blackboard, no? Just in case, no. Okay, then I will. Well, here. Great. Great. Okay, so we'll recall this in due time. But something is. Pardon me? Okay. So, the Galois group of K over K is consists of the powers of Frobenius. Okay, and hence this inner sum over the non-zero elements of our degree M extension, Pm of x tilde times the product over Galois group, 1 plus t theta of gamma x is equal to the sum over all subsets in the Galois group, t to the power cardinality of this subset, the sum over all non-zero elements, p tilde m of x, the product over elements of this subset, theta of gamma x. Okay, and this is equal to the sum minus 1 to the power m minus 1 over all subsets, t to the power cardinality of the subset, p tilde m of theta mi, where theta mi is the character x goes to the product over all elements in the subset, theta of gamma x, okay, well, so this character lies in the set of characters, the dual group of M and M. Okay, and so again, the conclusion is that the logarithm of h tu is the sum over all positive integers minus 1 to the power m minus 1, u to the power m over m, the sum over all subsets in the Galois group, t to the power cardinality of the subset, p tilde m of theta mi. Okay, we will also need this conclusion. Now we denote the Galois orbit of the character theta mi in Lm by phi mi and now let's prove one last lemma that for any r less than n, the coefficient of t to the r u to the n in h of tu so we know that it is an integral element, but it is also equal to the following expression: the product over S and J of the sums over all positive integers, elementary symmetric function Em of phi S J times t to the power sorry, maybe I should, again.
To find a eraser on the left.
Pardon me?
Okay. Plus, plus and maybe.
Plus, yes.
On the left blackboard there.
On
are
blackboard.
erasers. On the left blackboard there
Yes.
are erasers. Try to use the left. It has an eraser next to the pencil.
What?
Eraser.
Eraser?
Yes.
Here.
It's
ready. And now?
Yes.
Oh, incredible. I don't know. It only worked once. Okay, and how do I return to the normal size? 74. Here. Yeah. So the function itself is this. So t to the power cardinality of j, u to the power s, and everything to the power m. Okay. So the coefficient of this is an integral combination. Well, in beta n. So we already know that the coefficient of any coefficient of this counting function is an integral combination. So the point of lemma is that the counting function h can be written in this form. So its logarithm is the product of logarithm, is the sum of logarithms of this. Okay, so proof that the Galois group acts on the set of its subsets. So we say that a subset I is primitive if its stabilizer is trivial, also is trivial, well, it's usually trivial, but for example, if it's z mod 4z, then the subset 0, 2 is non-primitive, right? Because when you add by the square of the generator, it's translated to itself. Yeah? And the pair M and the subset is called an index. Okay. Then all the shifts of I are distinct. And the Galois orbit of I consists of m elements. Otherwise, the stabilizer in the Galois group of I is a certain subgroup by certain power of Frobenius for a certain divisor of the group, and I is the union of cosets H times J, and J is just I mod each, and so it lies in the quotient Galois with H, and now J in this quotient, which is the Galois group number S, is already primitive. So all the symmetries I possessed are quotient out, and so S and J is an index in Green's terminology, and theta mi is the composition of theta S J with the norm map from M to S. From M of M to MS. So in the dual group, in the L group, that was the union of duals with respect to the dual norm maps. So this means that the corresponding dual things are equal. Theta mi is equal to theta Sj in L. Now the Frobenius Galois orbit phi Sj consists of S elements, and hence our renormalized power subfunction Pm over theta mi equals P m divided by S over phi Sj. Okay. Now we had an equality. So let me rewrite it. The logarithm of h u was equal to the sum over all positive integers, -1 to the power m minus 1, u to the power m over m, the sum over all subsets of the Galois group, t to to the power cardinality of this subset. The normalized power sum theta mi. Here this was this quality, and it implies that the logarithm of our counting function is the sum over Sj, the sum over all indices. The sum over all positive integers, minus 1 to the power m minus 1 over m, pm over phi plus j over t to the power cardinality of j, u to the power of s, the power of m. Okay, and the sum is over the set of all indices modulo shifts. Okay, and well, this means that Sj is equivalent to Sj prime if the orbit, the corresponding orbits coincide. Now the generating function of the power sums p of negative t is the first derivative of well, the logarithmic derivative of the elementary symmetric function, generating function. We conclude that the sum over all n minus 1 to n minus 1 over n pn over phi sj t to the cardinality of j, u to s to the power n, sorry, is the logarithm of the sum over all positive integers, elementary symmetric function em of phi sj over t the cardinality of j, u to s, and to the power m. Oh, no. Sorry. What did I do?
No, снизу там X.
X. Yes. What the, yes.
It's red.
Well, it's not so bad, but
At least it's ready. It doesn't red. No, I think
Можно направо ехать.
а?
Можно направо ехать. Ты можешь направо закрыть это, но не можешь поднимать просто.
Ну, сейчас ты можешь сделать что-нибудь сказать?
Что потеряет?
Ага.
Сейчас. А, вот. Хотя бы одна есть.
Okay, thank you. Thank you very much. But the left blackboard doesn't work.
Это можно правильно. Нет. Да. Вот еще раз напоминаешь?
Okay.
Можно сдвинуть, чтобы плюс
Yes. Okay, so maybe let me claim that we proved the left. Well, so we proved that the coefficient of t to the power n, u to the power r, or maybe vice versa. And now how do I erase? But again, that doesn't matter much. In the generating function, the product over all s z, the sum over all positive integers, em of phi sg, to the coordinate of g, u to s to the power m, lies in Bn. Okay. Now the corollary is that given a Frobenius orbit phi in consonant in L, of cardinality d, and a positive integer, E n of phi is the characteristic of an integral combination of characters of G dn. Okay. So I mean, we produced certain combinations like this that were integral combinations of characters. They were characteristics of the integral combinations of characters. And now we want to express the most basic elementary symmetric functions as a certain integral combinations of those coefficients. That's our next aim. So let's try. So we'll try to do this by induction in pairs N, D with lexicographical order. And D is smaller than N prime D prime if N is smaller than N prime, or N equals N prime, and then D is smaller than D prime. So let's do first the base of induction. When N equals D equals 1. Then we deal with GL1, just a multiplicative group, and with its characters. So the orbit phi consists just of one element, psi. It is a character from N1 to C star. And then E1 of psi is equal to P1 of psi and is equal to P1 of psi is equal to just some overall multiplicative group psi of x, P1 of x, and that's just the characteristic image of psi. Okay, and that's good. Only something to start with. So we wanted to study the characters. Yeah, we proved that the character of GL1, the usual one-dimensional abelian character, lies in the lattice of characters. The corresponding characteristic is lies in the integral lattice. Okay, now well, induction step. or denote the coefficient of t to the power n, u to the power n d in h of t u by chi n d. So according to this lemma, this chi and d is the characteristic of a character of G and D. And also we know that chi and D is the sum over all V, the product over Sj, the indices, E V of Sj of phi Sj. So the sum runs over all the positive integer value functions V on the set of indices such that the sum over all the indices, the cardinality of J times V of Sj equals n. And also the sum over all Sj, S times V of Sj equals Nd. Now, do I just erase everything, yeah? And continue, yeah. So for all the indices in this sum, we have V of S J is at most n, and S is at most D for V of Sj equals n. It means that in our lexicographical order, V of Sj and S is at most Nd. And the equality only holds when V of Sj equals n. It implies that the cardinality of G equals 1. And S equals D. Okay, hence the leading term of kind MD equals En of phi D, and then just the subset consisting of 1. Integral group. And the orbit phi and D, sorry, phi D 1 is the Frobenius orbit of our kind of theta preceded to MD. Okay, so we choose theta such that theta on MD is just phi. Then chi MD will be equal to E n of phi plus smaller terms, meaning products of at least two well, E functions, elementary functions, but those by the induction assumption already are the characteristics of characters of G and prime D and prime D prime for n prime D prime smaller than ND, and we're done. Okay, so today we again had some ugly combinatorial preparations, but next time I think we will just finish, because we constructed a basis, a nice integral basis in our ring of characteristics of symmetric functions, namely the elementary symmetric functions, and hence everything else, which is usually a basis, will be a basis as well. For example, Schur functions. And now we already know that they form of normal basis, and the only thing to check next time will be that they are positive. You know, their values of 1 are positive. Then necessarily must be characters. And that will be it. Thank you. Yes. Thank you. Loosely, yes. Loosely cells, I difficult to understand, but you don't. Well, depends on what you want. Finish this.